Swayam Prabha. Digital India. Educated India.
So, in this lecture I am going to primarily focus on 3-phase equilibrium for the ternary system. Before that, let me just tell you about this variation of the isomorphous ternary phase diagram. You know, there are many ternary phase diagrams where liquid phase undergoes phase separation, just like a monotectic reaction. In a monotectic phase diagrams, we know liquid phase undergoes separation from one liquid to two liquids. Same thing is also possible here, correct. And two such variations I am going to discuss. One is that in which on the binaries, suppose AB, okay, for it liquid undergoes a phase separation, and because of that there is a maximum in the, you see here these are the two, okay, let me just tell you, for the both the ends, for the AC and BC, here AC is having this again length separate phase diagram, one is like this, other one is like that, and BC is also like this, but only AC shows a maximum, okay. What is that? It is, this is like this and it merges here and then it moves, correct. So, basically this is a congruent melting liquid, not a separation in liquid state, whatever I told you that is not correct. So, what is the way is basically, if I say, if I draw AB phase diagram binary, this will be like this, correct. So, this is what I am talking about it. If I have a maximum of point in the AB binary like this, then how it will look like? This phase diagram will look like this, a ternary space model. And if I project it, this will be like this. You have alpha and then liquid, and this is alpha plus liquid. And these are the tie lines possible at a temperature. If I project it from the top, actually, if I project these liquid surfaces, liquid and solid surface will look like this. Now, this is one variation which is seen, okay. Second variation is that I can also have situation like this, which I was telling to you, okay. All the three binaries will be isomorphous type like this. This is one isomorphous, there is another isomorphous, and third one is also shown, okay, it is isomorphous. But the inside the ternary means inside the ternary triangle, the liquid actually develops a miscibility gap, and this because of that there is a dome, okay. In a monotectic system you have seen, no, right, there is a dome like this, correct. This is the dome in monotectic system we have seen. So, instead of that, this particular thing is present in the ternary system. So, therefore, this surface has a maximum point like this, okay. This is the maximum point and it slopes down. This is seen, this is basically nature of immiscibility, correct. So, immiscibility exists over a composition domain like this, immiscibility exists, correct. Similarly, you have immiscibility exists from this part to this part composition, you can see here exist. We are not discussing in details about that because these are out of the domain of this syllabus of this course, but these things are already there in the books if any interested reader wants to know, they can discuss, they can read it and understand it carefully. So, now I am going to move on to the section which is important, or what is known as the ternary 3-phase equilibrium. Okay. Now, in a binary system, what is the meaning of 3-phase? You know, 3 phases can coexist in a binary system when the degrees of freedom is 0, like in a eutectic. In a binary system, you have a eutectic liquid going to alpha plus beta. 3 phases can coexist in a eutectic phase diagram, or a peritectic, or a syntectic, or a monotectic. Okay. And this is represented by a horizontal line parallel to the compositional axis. We represent what as a horizontal line. This is a eutectic temperature here. Now, this is distinguishing feature in a ternary phase equilibrium is that, because it is in a ternary system, this is f equal to 0, right, degrees of freedom equal to 0. In a ternary system, f is equal to 3 minus 3 plus 1, that is equal to 1. So, f is monovariant, system is monovariant. If system is monovariant, then it occurs over a temperature range. It cannot be at a point, or cannot be at a fixed temperature. In a binary system, degrees of freedom is 0, because of that your temperature is fixed, composition is fixed. This is a composition, this is temperature. You cannot change any of this. But in ternary system, you have 1 degrees of freedom, and let us suppose, and that is why we say that these 3-phase equilibrium in a ternary system can occur in a temperature range. Okay, understood that. It occurs over in a temperature range. Now, for any of these 3 phases, as the composition of the 3 phases generally vary with temperature, obviously alpha liquid and beta will vary with composition temperature. So, we can represent equilibrium by 3 curves. 3 curves is what? One is alpha alpha 1, remember one is alpha alpha 1, other one is what? Other one is beta beta 1 and L L 1. Okay, I will explain you what. At temperature T, 3 phases alpha beta liquid are at equilibrium. So, therefore, lines alpha beta, alpha L and beta L will form a triangle, correct? It will form a triangle. How? Okay, let us look at it. This is can be done like this. This is beta alpha liquid, correct? So, now as the temperature goes down, we can represent the whole system like a triangle, set of triangles. Okay, these are set of triangles. I have drawn only 2. Okay, so one can draw many of them. Okay, so set of triangles. Okay, so this is liquid, this is at the top, and I think let me just draw a little bit better way. Okay, so that is the idea. So that means what? LBL is a triangle. We can represent this whole thing by a triangle. Now let me explain from the space model. As you see here, the space model has they have everything here, A, B, C, okay, and you have 2 binaries, BC and AC has eutectic reactions. Okay, there is a binary eutectic, there is a binary eutectic there. Okay, you can clearly see, this is a eutectic point, there is another eutectic point here. So, but on the other hand, AC has isomorphous binaries. Okay, so therefore, in a binary eutectic system 3-phase, we draw a horizontal line to show 3-phase equilibrium, correct? Here also between AC also a horizontal line, red color. Now in a ternary system, we show this equilibrium by a triangle. That is what is shown between liquid alpha and beta here. You can see here this is a triangle, correct? And this triangle actually goes over here. Okay, this is what is this triangle. And this is therefore the whole equilibrium is discussed as a stack of triangle as you decrease the temperature. As you going down temperature, the triangle is shape is changed. That is what I showed you. So therefore, if I this is what is my temperature, and this is how the triangles will keep on changing. Basically what will happen as the composition changes, so composition of the three phases will keep on change as a function of temperature. This triangle positions of each of the vertices of the triangles will also change. This is much is very important for you to understand. Okay, I think that's needs to be very clearly understandable. Otherwise, whatever I am going to discuss, complex shapes will not be clear to you. So that's what I am going to do in the board. So what I am going to say is that in a binary, very carefully try to understand, in a binary 3-phase equilibrium, okay, temperature, three-phase equilibrium is represented by a tie line, by a horizontal line. This is for eutectic. For a peritectic, one can actually draw that. So both the cases, the three-phase equilibrium, liquid going to alpha plus beta here, liquid plus alpha going to beta here, are represented by a horizontal line parallel to the x axis. That is what is done. But in a ternary system, you can't do that. Why? Because in a ternary system, the reason we can do this in a binary system is because f is equal to 0. Why? Because f is equal to c minus p plus 1, c is 2, p is 2, 1, sorry, c 3, that is equal to 0, correct, 3 phases. But in a ternary system, for a ternary system, for c is equal to 3, f is equal to c minus p plus 1, so 3 minus 3 plus 1, that is equal to 1. It is a monovariant system. That is why you cannot do it, because it is f equal to 0, this point and this temperature are fixed here, that is why, but there it is not fixed. So therefore the whole thing will take over a temperature. The temperature, this 3-phase equilibrium will be taking place over a temperature range, not at a fixed temperature like a binary. So how to represent that? That is what is the most important thing I need to discuss with you. That can be represented simply by a triangle, okay. This is the triangle at a temperature T, okay, T equal to T1. Now I can represent the whole thing correct in a series of triangles. Oops. Series of triangles like that. Obviously, the way I have drawn, so this is a function of temperature. The way I have drawn is that all the triangles looks like similar, okay, they may not be, they may have different shapes not in different shapes, different sizes. Obviously the one which will be sitting at the bottom can have larger size. Now let us get back to this phase diagram. Hopefully you have understood this part. In this phase diagram, I am saying that I am going to represent this whole thing feature as these alpha beta, liquid plus alpha plus beta triangles, correct. So you see here the liquidous surface is much complex here by compared to the isomorphous system. Liquidous surface is shown here, written here, this is the liquidous surface, it is very complex. It's on the left side it is same, but on the right side it is like this, on this side it is like sorry, it is very different, okay. I have to draw a little bit more, it is like that. In isomorphous system it was like this surface. So completely different liquidous surface, correct. Similarly solidus surface will be like quite a bit different. So as you see, simply going from 2-phase equilibria to 3-phase equilibria, the whole 3-dimensional construction gets quite a bit changed, and one needs to really look at this. Secondly, we need to also look at the solver surfaces. Okay. So, what are the solvers? In a binary you have solvers, these are the solvers. Okay. This is solvers, this is also solvers. What does the solvers, what do the solvers tell about you? They tell you how the composition of the alpha and beta phase is changing as a function of temperature. Similarly, here also they are going down as you see here. That means as the temperature decreases, beta is becoming more rich and rich B, alpha is becoming more and more rich in A or C. So, if that is what is evident, so that is why the triangle will expand. Okay. As I showed you, one triangle at the top, one triangle at the bottom, I am showing you triangle has expanded, it is becoming bigger and bigger. So, therefore, these the construction can be represented by this. Okay. There are many such things. Let us just show you, let me just show you these 3-dimensional features. Okay. Today. So, 3-dimensional features are like this. I am just going to show you this zone first, alpha. If you see alpha, alpha has this much of C, this much of B rather, okay, this much of B, this is C end, and then it goes like that, correct. Similarly, this is goes like that, then it is coming isomorphous, and finally it is meeting there. This is one geometry, this is the alpha phase field, primary alpha phase field. What is the primary beta phase field? This is also like this part I have drawn, this part, okay, it is like this, again going down here, triangle, correct. That is how it looks like. So, there are the two primary phase fields, very easily detectable. Now, alpha plus beta phase field is basically like a extended triangle. You see here, this is a triangle, little bit not triangle, this is a trapezoidal shape, okay, little bit. This is what is at the room temperature, okay. As you go along, this is the vents, and these are the tie lines, okay, drawn in on the surface, correct. This is alpha 2 phase region. What are the other 2 phase regions? Liquid plus alpha, liquid plus beta, liquid plus alpha. Liquid plus alpha is like this. This is again a trapezoid, okay. You can see here, this is what is a triangle. Trapezoid. And the easiest one is liquid plus beta. This is again I do not know what is the shape can be called. It meets at the center. This looks like a pyramid, okay, correct. So, but liquid plus alpha plus beta, that is what is more important, it is like a lot of triangles, correct. All the triangles are shown here exactly the way I have drawn in this picture. So, these are the 3 different, these are the different phase, one is single phase alpha and beta, second one is 2 phase liquid plus alpha, liquid plus beta, or alpha plus beta, and liquid plus alpha plus beta is consisting of these triangles, correct. And again I am showing you, okay, you can see here that these are the for the binary eutectic, this is for the binary eutectic on the alpha plus beta here, okay, and this is for the, these are the tie lines corresponding to that. So, this is the whole triangle, okay, shown here from top to bottom. So, one can actually draw tie lines inside and show that. Am I clear? I hope this construction is understandable to you. Now, one can actually show, one can actually discuss even, one can actually discuss even the certification parts of these, but I am not going to do it today. I am just going to discuss with you how the things can be become shown. So, solidification of these alloys, there will be three different types of alloys for which we have to discuss solidification. One, whose composition will lie well inside the alpha or beta thing, that will be same as what I discussed for the isomorphous system. Well, let me just tell you the binary, then it will be clear to you. In a binary, normally we can discuss 3 different types of alloys, okay. So, one is this, other one is this, and third one is this or this. So, what are these called? This is eutectic, these are hyper or hypoeutectic, and this is well inside this alpha phase field. Same thing here can be done. So, we can discuss alloy composition with same as eutectic, one of the eutectics. We can discuss this alloy composition little bit away from the eutectic, but well within the two phase region, and third one is obviously same as I told you just now for this within the alpha. So, you have alloy composition given by this or this, another one is given by this, and third one is given by this or this, okay. But well inside the triangle, not on the binaries. So, there are different ways one can discuss. The first one, which is what is the same as isomorphous, is basically for the alpha or beta phase field, which I will not discuss. For the alloy composition with eutectic, well, the solidification actually depends on which eutectic you are considering. Obviously, it is a 3-phase liquid, 3-phase solidification zone, but we are going to talk about only the 2-phase things, that is this one, which is little bit away from the solidification. Here again, obviously the liquid will hit the alloy composition will hit this liquidous surface, and then one can actually draw, this is a liquidous and this is solidus. So, one can actually draw the solid. So, you can see here this is the tri-line, and slowly as the temperature goes down, this is what will happen, correct. Finally, as the temperature will reach, this is the solidification will be over, correct. So, if I draw it on a this projection I have not shown you. So, this is will be this is my liquid. So, liquidus will be following like this, and solidus will follow like that, and it will solidify. So, again this is L, this is X. So, this is L4, L3, L2, S2, S4, S3, S2, okay. That is how this is S3, okay. So, one can actually follow exactly this sequence and understand the solidification. But for the eutectic, it is not going to be the same, which we are going to discuss in the next class in a detailed manner. But for the time being, I request you to look at these shapes, different shapes which I have shown you in the class today. These shapes are basically vital for us to chalk out these solidification pathways, understand these phase transformation behavior. So, with that we will take care of these rest of the part in the next class.